one. So a bit of concentration, but we'll be short. Well, I'm talking about gravity theory of noncommutative spaces. This is about joint work with Paolo Aspiri, Christian Lohmann, Maria Dimitrijevic, Peter Schupp, and Julius West. It is a nice and large international collaboration, and well, our first results we published in this preprint, and I will talk about some more details of this, what we published in this preprint, or you have heard already some ideas of the generalized things to more general stuff about Paolo at this point. So, here I will be very short. In the introductory part, you know already everything, but to fix the notation, I go through this very fast. So, basic idea again is that the coordinates at short distances should not commute. So, the commutator of the coordinates is given by some function depending on the coordinates, which we call theta mu, Meyer called it J. And our algebra of non-commutative functions is given by those formal power series in the coordinates respecting these commutation relations. So we give up the concept of a differential manifold and come to this non-commutative algebra instead. The easiest example, which I will consider in my talk, is where on the right hand side we have constants. So this is what was already called the so-called canonical deformed quantum space, and I will tell you how we constructed gravity theory on this space. Well, so this space has a nice feature. It has the noncommutative property. That means that I can have an isomorphism from the commutative side, where I have functions depending on commutative variables. These are polynomials. Theta is our deformation parameter. And well, I have a lot of ways to define such an isomorphism from the commutative algebra to the non-commutative one. And this one we call an ordering prescription, for example. Having such an isomorphism, I can define a new product on the algebra of commutative function by pulling back the non-commutative product on this side using this vector space isomorphism. So I define a new product, f star g, by just first mapping f and g to the non-commutative side, which we know was a hat, and then multiplying them there, where the multiplication is non-commutative, and then going back with the inverse of the isomorphism. I tell you this because this can of course be done also for more general structures, not only in this constant theta case, but here things are especially easy. The result, if you do such a thing and you take as an ordering prescription the symmetric ordering, you will get the Meyer-Weyl product, which you have seen already several times. So this is the star product, which you get for such a space. But okay, I just say very short. Of course, it's not unique, but depends on which ordering prescription you choose. But we will take it here in our example. Well, having a non-commutative algebra, you need a differential calculus. I don't want to say a lot about that because you heard about it. You can always find such a calculus. Let me just say that derivatives are maps on the algebra. So it's a map which is defined from the algebra to itself. Especially it has to respect the commutation relations. Yeah. In our case of the canonical structure, things are very easy. There we saw already that the usual undeformed calculus is a well-defined map on this non-commutative algebra. So things can be, of course, a lot more complicated when you have other structures. Okay, let's stick to this example. It's quite easy. So we have our non-commutative algebra with the canonical structure, and we have the undeformed calculus, which is a well-defined map on this algebra. So now coming to gravity theory, we want to construct something which is invariant with respect to infinitesimal diffeomorphisms. So diffeomorphisms are generated by vector fields which satisfy such commutation relations, so they're close. Vector fields, commutator of vector fields is a vector field again. Well, our aim is now to lift operations like vector fields to the non-commutative algebra. Well, that's what I've said. What I've told you before. This can be done easily because I have calculus. I know how to multiply my non-commutative algebra, so I can just define a map by acting on f, by first applying such a derivative d rho, and then multiply with the coefficient function psi rho, and then summing over rho. That's certainly a well-defined action on my non-commutative algebra. The point, yeah, okay, and what I want to tell you that, well, okay, that's a well-defined action, and using the ordering prescription which I showed you before, this can again be pulled back to the non-commutative setting, and it's given by something that we call star action. That's quite easy. So just take the coefficient functions rho of the vector field and star multiply it with the function where I first act on with my derivative d rho. So this is a natural way to introduce a star action by putting back this natural action on our algebra. Okay, so now let's take such a commutator of two those vector fields, and you will see that in the non-commutative setting this does not close. So this is not a vector field again. You see here appears a star commutator of the coefficient functions, which of course vanishes in the commutative limit, but not in our non-commutative setting. So what do we want to do? Our aim is we want to define higher differential operators by requiring that we have that such a commutator relation actually closes. So we want really to find representations of this algebra equation. And the solution can indeed be found, well, it's possible to find a solution to it. So the unique solution, but this is a solution which has nice features. And it's given where this expression where I just give you the first order formula. So you see that this is a higher differential operator which starts with the usual vector field psi in the zeroth order, and then you get higher order deviations in the deformation parameter theta. At the first order, this thing looks like that. Of course, I have higher order, infinite orders of theta, which I skipped here. The closed expression is not complicated, but so you see everything perturbatively to first order here. So now I can take such a higher order differential operator. I claim that it closes to order and satisfies these commutation relations, and I have a natural way how to act on my functions, my commutative space of functions, by the star action which I just introduced transparently before. And if you calculate everything out, actually the action, what comes out, if you really take the star action of this higher differential operator of functions, if you calculate everything, what comes out is just the uniform action of our vector field. So in this case, I mean the action is really uniform. So having such a differential operator, satisfying our commutation relations, I can ask how does it act on a star product of functions. And this now, here happen non-trivial things. I mean, acting on a star product of functions, one can just calculate what happens, and it's not satisfying the usual Leibniz rule. So what I get here is really the operator acts on f star g plus f star on the operator acts on g, and plus additional terms which are modifications to the usual Leibniz rule. Again, I give you only the first order terms. You see, everything is perturbatively written here in theta. If theta goes to 0, everything goes to the commutative setting. Well, this one can instruct this deformed Leibniz rule. One can instruct it to non-trivial coproduct rule, which I wrote here, which basically tells us how to act on a product of functions. For those that are not familiar with the well, so to construct a physical theory, we now want to introduce scalar vector and tensor fields, which are representations of diffeomorphism algebra. So first we introduce scalar fields, which should have, which are defined by a certain transformation property. And the transformation property, infinitesimal transformation property, should be given like this. This is our definition. So scalar field phi is a scalar field which transforms like that. So I take my differential operator, get like psi, acting on f. So, and this variation operator we attach with this new coproduct, the deformed coproduct, which I gave you again to the first order, and having this coproduct assures that the product of two scalar fields transforms as a scalar again. So if I transform this star product of two scalar fields using this deformed coproduct, it's just constructed in the way that our star product of two scalars is again a scalar field. This is the basic point, which is the non-trivial thing what happens. In a similar way, one can of course also introduce vector fields, and, tensor fields, and so on, and get all the representations of this of our algebra. So let me shortly summarize what I said. We consider so-called theta deformed diffeomorphisms, infinitesimal diffeomorphisms. The algebra of our diffeomorphisms is undeformed by construction. So it satisfies this the algebra relation, this commutator relation. But the co-algebra is deformed. And the full coproduct is given by this expression to all orders of theta. One can now introduce scalar fields and tensor fields as representations of this deformed diffeomorphisms. And let me remark. So this is the abstract Hopf algebra. This is the abstract Hopf algebra of infinitesimal diffeomorphisms which we consider. And depending on what kind of representation it acts, the representation is given by differential operators. So for example, if I act on scalar fields, then my representation is given by exactly this differential operator capital X psi, which I showed you before to first order. If I act on vector fields, then it's a different representation. Okay, so this is the basic setting. This is the basis of our building up a gravity theory. Having this, one can now introduce geometry on this space. So to do this, we need a metric, and we define a metric to be an object which certainly should reduce in the theta goes to zero limit, the classical metric, so it has a reasonable classical limit, and it should be a tensor of rank 2. It should have the right algebraic properties with respect to our deformed diffeomorphism algebra. And where such an object we can construct, for example, by using a set of vierbeins. This is just meant as being a set of 4 vectors, in A labeled by A, and this symmetrized product of those vierbeins. So, because of our coproduct of our deformed version of the diffeomorphisms, this product of 2 vectors indeed transforms as a tensor. So this object, which we wrote here, indeed has the right algebraic transformation properties as being a tensor of rank 2. And if the vierbein is such that it reduces in the classical limit to the classical vierbein, it also will have reproduced the classical metric. So to raise the lower indices, I need a star inverse of this object, which we define like that. So a capital G with upper indices, which is just the inverse of this matrix with respect to the star product. This can be found and can be constructed explicitly in terms of the classical inverse of this capital G menu, order by order. So let us now assume that we have a symmetric connection, then demanding that the covariant derivative I have to introduce here, but sort of have enough time for all the details, but just demanding that the covariant derivative on this metric, which is given by using the differential and the symmetric connection here, demanding that this should vanish gives you an analogy to the commutative setting, gives you a unique expression of this Christoffel symbol in terms of the non-commutative metric and its star inverse. So you see I have my Christoffel symbol. It is expressed with respect to the non-commutative metric, its star inverse, and all operations here are algebra operations. The star term, which is an algebra operation, and here's a star action of our non-commutative derivative, which amounts to the uniform one. But all this here is fully full operations in the non-commutative algebra. So, well, now having those covariant derivatives, I can calculate a commutator of two covariant derivatives to get a curvature and a torsion. This can be done. And well, the nice thing to do is, and the interesting thing to do is, to express the curvature R first in terms of all the non-commutative quantities like metric and like metric, and later then expressing all the non-commutative quantities in terms of their classical counterparts. Well, I don't have time to tell you in detail how this works, but I show you just to give a taste of it. What is the result for the curvature tensor R mu rho sigma? This is now written after first order in theta. The zeroth order is the uniform object, and in first order theta, you find it expressed in terms of the uniform curvature, the uniform metric, and the uniform Christoffel symbol. Yes.
Why do you have some places with Christoffel symbols and some places with the can't you express it only in terms of Christoffel symbols or does it only add up to something covariant looking?
No, well, I'm not sure if I cannot probably, I think I cannot write it fully with only using Christoffel symbols. Well, I mean, this is what comes out, but certainly you can do some modifications, shifting some terms and things like that. Well, I'm not so sure about this here now because more interesting is the curvature scalar. Okay. But you cannot express it only using the Okay. Well, what we can do next is defining Einstein-Hilbert action, a deformed version of an Einstein-Hilbert action, and the aim is to define an action which should be invariant with respect to this deformed diffeomorphisms which I introduced. So to do this, I need a measure function which has to satisfy some transformation properties in such a way that it makes this integral invariant. I cannot present you details here. So this measure function we call E star. It reduces to the classical limit to the usual square of G. And so the richer scalar I can also obtain just by taking the curvature tensor which I showed you before and contracting the indices using the metric that we have. And well, I can indeed define such an extension by using the usual integral and the star multiplication of the scalar R with the suitably used measure E star. Well, we know that this thing here will not be real because our scalar is not real. This measure is a real object, but the scalar not. So what we do is just we add the complex conjugation to this expression to get a real action. So let me say again, this now is a real information of the Einstein-Hilbert action. In the classical limit, it reduces to the usual Einstein-Hilbert action, and it is invariant with respect to the deformed diffeomorphisms that are introduced. Since the integral is cyclic, in the case of the star product we use. One can also make some short modifications and ends up with the integral over the star times star multiplied with r plus its complete conjugation. So I'm finished. Let's summarize shortly. We have constructed a theta-deformed version of our diffeomorphisms. This was the basic ingredient for the construction of our gravity theory. Having this theta-deformed version of diffeomorphisms, one can construct representations of it, like scalars, vectors, and tensor fields. This theta-deformed diffeomorphisms acting on scalar fields are represented by higher order differential operators, which are denoted by this capital X psi. And all this is given explicitly to all orders. One can introduce covariant derivatives and define a curvature tensor. After that, we introduced a metric, and we got a curvature scalar, which gave us the possibility at the end to construct theta-deformed diffeomorphism invariant Einstein-Hilbert action on this space. So we got a gravity theory on this deformed space, which may, and what we did here, all the construction can even be general. Well, I did it for a theta constant case, but we saw already how one can generalize it to more complicated star products coming from twist. And at the moment, we are even working how to do it for structures coming from concentric star products. So thank you for your attention.
Are there questions? Excuse me. What are the observables of such kind of models? So in astronomy, we do real numbers, angles, distances, and you have objects with values in some non-commutative algebra.
Okay, I mean the objects are not commutative objects, but what we are able to do is express all the objects in terms of commutative variables. So our basic input is a field line, and we can express everything in terms of the commutative classical field line. And we just get deformations with classical theory order by order and theta. So we can write down this action, Einstein-Hilbert action, expand everything as we explain with theta how it works. But then you would get a zeroth order, which is the classical Einstein-Hilbert action, and first order contribution, which also contains fields that you know everything expressed in the field line, but additional terms which usually don't appear in the classical theory depending on this information parameter theta.
But basically you get real numbers. So
well, yeah, I mean, yes, but I mean, you would have to know what theta is. I mean, theta is a formal information parameter. This is your job.
That's another question. From what I know, at least in the linear approximation, the gravitational field is connected with a certain representation of the quantum directive of zero mass and helicity 2. This is a very important value principle if you want to construct a quantum. Do you have something similar with some quantum analysis?
Well, the quantum analysis has been introduced by Maria 2 days ago, and this works with the very same framework. The construction here is just more general. So I mean, what we did here for diffeomorphisms, I mean, the quantum basic transformations are just a subset of special vector fields which are linear in the coordinates x, and this can be done. And Maria introduced it in detail 2 days ago.
Other question, please.